So Charlotte is a postdoc currently with the Institute of Neuroinformatics at the University of Zurich and ETH Zurich. She works as a postdoc researcher looking at low power and high density spiking neural network design, and she aims at bridging the bottom-up and top-down design approaches towards neuromorphic intelligence, which is also the topic of the talk she will have here today. So Charlotte, the floor is all yours.
Thanks a lot, Peter, for the introduction. Thanks a lot to the committee for inviting me to present this research, and thank you all for being here. So in this talk, my objective is to provide you with a global overview of the field of neuromorphic engineering, together with the key trade-offs, design choices, and methodologies that can be adopted in the field, and finally with the results that we obtain with our own specific set of constraints. So first of all, let's assess quickly where we are in the pursuit of intelligence. So we can take here the example of the game of Go, so a famous example, but yet still a very good one because the number of possibilities in this game just exceed the number of atoms in the universe. And yet we have seen that the progress in artificial intelligence system has been quite fast, from the first computer to defeat a professional player, to the first computer to defeat the world champion, and finally to the one that is now completely out of reach from any human player. And therefore, I wouldn't be surprised now in 2021, given the pace of increase and given also a dedicated hardware implementation, that we could come quite close to the efficiency of the human brain on this very task, because that's the problem that we have. Here we have computers that really excel at solving one specific task, and we have the human brain that is just here at very low power and area overheads, is able to adapt to a huge diversity of tasks and environments, and therefore there's still a barrier that we could call the cognition. And if we want to uncover what's in there, we can explore bio-inspired computing. But the problem that we have is that if we simulate biological neurons on conventional digital computers, they will lag about 7 orders of magnitude in size and 5 orders of magnitude in power behind the biological counterpart. So in order to get there, that means also we can't rely solely on Moore's law, especially as technology scaling trends are leveling off. And therefore, we may need a paradigm shift, and that's exactly what neuromorphic engineering is about. So neuromorphic silicon neurons lie approximately there for the moment, and this paradigm shift is twofold. The first paradigm shift is along data representation, so from clocked multi-bit to sparse event-driven spike trains. Spike trains are represented here as a qualitative overview. And finally, along the architecture, so from really separated processing and memory to a distributed form of processing that collocates neurons and synapses, and therefore that collocates processing and memory. And that means we still have 2 open questions to solve in order to achieve this paradigm shift. The first one is, how do we get there? So there's still an efficiency gap. So what are we currently missing? And the second one is more of an open one. We have that artificial intelligence is supported by conventional digital computers, and natural intelligence is supported by the biological neural networks. And therefore, how do we go from one to the other and uncover the concept of cognition? Or how do we uncover this way the concept of neuromorphic intelligence? And therefore, we had that the neuromorphic community has adopted a huge diversity of approaches to try to solve these 2 challenges. And we'll review them qualitatively quickly here. So first, we have the sub-threshold analog approach, among which the ROLLs, the Dynapse chips from the Institute of Neuroinformatics, and the Neurogrid systems from Stanford. And if you haven't done so already, I really encourage you to check the tutorial that was done by Professor Indivri on Monday, because it's exactly about this design school. And you have seen also in this tutorial that you have really a nice property of direct emulation between the physics of the MOS transistor operated in the sub-threshold regime and the dynamics of the ion channels in the brain. It's really the same physical mechanism, and therefore you can benefit from a direct emulation in biological time. And therefore these circuits are ideal for basic research. Next, you have the above threshold analog systems, among which wafer scale, brain scales 1 and 2 systems. And these systems benefit from an acceleration factor of about 1,000 to 10,000 compared to biology. And therefore, that means that these systems are usually used for neuroscience simulation acceleration. And I told you that these systems are mostly analog, but actually they are mixed signals. So the core computation is analog, and usually the spike routing infrastructure is digital. So if you go to the fully digital side, you've got, of course, the software approach running on conventional CPUs and GPUs. These are really the go-to approach for maximum flexibility, And yet you're still able to deploy conventional neural networks quite fast, but spiking neural networks usually run quite slow. So that's an issue, but you have maximum flexibility. If you go one step finer in the granularity of implementation, you have dedicated simulators based on FPGAs or distributed simulators. So here is the example of the Spinnaker 1 and 2 system that really relies on a distributed array of von Neumann processors. And these systems are able to retain a high flexibility while improving the power area footprints and increasing the simulation time, improving the simulation time. So actually, this is one step finer in granularity. We can go one step again finer in the granularity in digital designs. So here are the large scale ones, the full custom True North from IBM and Loihi chip from Intel. And these systems are usually used for cognitive computing. So cognitive computing is when you give away some biophysical realisticness to run large-scale functional abstractions of neuroscience-inspired networks. And finally, we have small-scale full custom digital designs, and that's exactly what we specialized in. So in these first two chips that I will present later, we are really seeking after bio-inspired edge computing, or should I say here bio-inspired tiny ML. And it's really experimentation platform. So you embed here a huge set of biophysically inspired primitives. And these platforms can serve as test beds for algorithms that you want to test to map them exactly on these biophysical primitives. And the third chip that we propose is Spoon, and it's suitable for low-cost adaptive edge computing or adaptive tiny ML. And now it falls into the realms of accelerators, dedicated hardware accelerators that aim at solving one specific task and improving the trade-off between accuracy, power area on this very specific task. And so I want you to remember two things in this overview. First, it's a qualitative, high-level overview. It's by no means an exhaustive one. For example, you have got some other references for this design school. But what I want you to remember is that here you can see there are really two ways to go. One that is strongly grounded on the neuroscience, and one that really wants to solve specific tasks. And therefore, if we want to summarize the methodology, two ways to go. The first one, you start from neuroscience observation, you implement neuromorphic processors that usually can be used for neuroscience-oriented applications, for example, simulation acceleration or basic research, as you have seen in the previous slide. And you can even use them to close the loop in an analysis by synthesis fashion. So this is what we would call the bottom-up design approach, leading to the design of experimentation platforms. And there are two key steps. The first one is to implement the building blocks, the neuron and the synapse. And the second step is to implement them at a large scale in silicon. And so the trade-off that you aim at solving here is really between versatility and efficiency. But the problem is that when you have a huge number of neurons and synapses on chip, what do you do with them? And that's a very difficult question, actually, especially in the field of neuromorphic engineering. How do we cross an efficiency gap to go to the real world application and more specifically demonstrate a competitive advantage on some real world tasks? So that's a tough question. So the other way to go is to start from the task that you want to solve, to implement a neuromorphic processor while taking into account insight from neuroscience. So this is now a top-down design approach leading to the design of dedicated accelerators. And the key two steps are first to start from the algorithms that solve this specific task, and then to implement them into silicon. So the trade-off now is between accuracy and efficiency. But the key issue here is, what do you consider as the key elements from neuroscience observation that you want to take and implement? Because that conditions the entire relevance and efficiency of the resulting device. So in this talk, we'll survey both the bottom-up and the top-down approach. We'll look at also the synergies in order to unveil roads to neuromorphic intelligence. And you have that these 4 points will be exactly the 4 points of this presentation. So 1, 2, 3, 4 for bottom-up and top-down. So that's also a good opportunity for me to take a quick break. Each time I reach the outline of the talk, I will take a quick break to make sure there are no ongoing questions. So far, there seems like it's not, but do not hesitate to ask them in the Q&A, and I will pause from time to time to make sure that there's no misunderstanding. Okay, so first step, bottom up, we look into the building blocks. So neurons and synapses, but first we have to answer one question. Should we go analog or should we go digital? And that's actually a very tough question in the field, and there's a lot of debate on it. And therefore, let's try to see what is best for which purpose. So we have the analog approach, and as said earlier, you can benefit from direct emulation approach from the biophysics of the ion channels in the brain and the physical phenomena that take place in the MOS transistor operated in subthreshold. And therefore, you have that you only need a few transistors to actually emulate a detailed biophysical neuron model. And so that means that the biophysical versatility over area trade-off is quite good. But the price to pay is that the design time is higher, technology scaling potential is lower. And there's this big question as to noise, whether noise mismatch and process voltage temperature variations is a bug or a feature. And you have seen also a lot on that on the tutorial on Monday. And therefore, on the other hand, we have the digital approaches that really do not emulate at all, they simulate. So that you need to implement solvers for the mathematical equations that model your neuron and synapse models that you have chosen. So that means if you have to implement these solvers, the biophysical versatility over area trade-off is really not good. It's orders of magnitude worse than analog. But on the other hand, you have a green light for all the aspects, and you can even have noise in a controlled manner if you want it. So the question that we ask ourselves is whether we can make the best of both worlds. And a pragmatic approach actually would be to try to make digital closer to analog regarding this trade-off. And this requires really stepping away from simulation. So you do not implement solvers from the mathematical equations that you want to model. You go for a phenomenological modeling approach. So you don't care about the equations, you implement directly the behaviors that you're interested in. And so that's what we are going to do for our neuron and synapse models. And actually, I'd like to come back to this later in this presentation in the perspectives to give also some perspectives as to what is good to do now and in the future. So now that we have to apply our phenomenological modeling approach to the neurons and the synapse, let's start first with the neuron. A good way to go would be to implement the 20 Isaacevich behaviors that have been observed in cortical spiking neurons in the brain. So there are really 20 of them. I won't dive into the details, but I want to emphasize here that it's really a bottom-up approach. We want to implement these behaviors in silicon, and once the device is back, we want to experiment with them. And actually, these kind of bottom-up experiments is also something that happens a lot in the two key neuromorphic workshops in the community, so in Telluride and Capocaccia. And for example, here are some examples we have experimented with. So for example, spike frequency adaptation can be used to introduce competition for unsupervised learning and winner-take-all networks. We have that spike latency can be useful for stereo sound source localization. We have that phasic spiking is useful for time-to-first spike encodings. And resonator is useful for the discrimination of specific frequencies. So these are just some examples that we have experimented with, and other developments are still going on. So it was just to make the point, it's a bottom-up approach. And therefore, if we now know that we want to implement these 20 behaviors, let's look at the state of the art. And we'll, again, not dive too much into the details, we'll look at it qualitatively. So we have this biophysical versatility over area trade-off. Here, biophysical versatility measuring the number of Isaacevich behaviors. Now, I told you it was much better for analog than for digital. Because here, do not forget, it's a logarithmic scale. So really digital is much less efficient than analog. Yet the phenomenological neuron that we propose lies here. So you see it's quite efficient to go for a phenomenological digital approach. And one important thing to know here is that these are all fully standalone neuron model implementations. So you can really replicate them in large parallel arrays. And one thing that you can often do in your morphic engineering chips, especially for digital approaches, is to go for time multiplexing so as to save a maximum of area. And if you want to time multiplex this neuron, so that means you only keep one update logic and all the states of all of your neurons are stored in one SRAM on-chip memory, for example, you end up with an area per neuron that is around here. So you see it can be really quite low. So I won't dive into the details of what is inside this neuron model, but I want you to remember a few key features. The first one is that the neuron model that we propose is entirely event-driven, so there is no time step integration. So that's usually the big problem of solver-based approach, and we get rid of it. And next, we find out that to implement the 20 Isaacevich behaviors found in the cortical spiking neurons, only 4 simple functions are necessary. These are threshold adaptation, time window generation, simple template matching, and membrane potential sign rotation. So that's all for the neuron. And now let's look into the synapse. And the synapse is a complex element because it's really the site of learning and plasticity in the brain. And therefore, we want to implement plasticity into these synapses. And if we look into the local learning rules inside the synapses, we have two main ones. We have spike time-independent plasticity, STDP, and spike-dependent synaptic plasticity, or SDSP. And qualitatively, for STDP, it looks into the relative timings between pre- and post-synaptic spikes. So if the presynaptic neuron spikes, before the presynaptic neuron, it's a causal relationship. And that means you can potentiate your synapse. If it's anti-causal, if it goes the other way, the post before pre, you will depress the synapse. So it's really enforcing correlation, causal correlation between the pre and the post-synaptic neurons. And that's what we call a Hebbian learning rule, neurons that fire together, wire together. And that's actually quite the same for SDSP. The mechanism is just a bit different. You look at the presynaptic spike, and each time you get a presynaptic spike, you look into the state of the postsynaptic neuron at the time of the spike. And it has one advantage. This is a learning rule that is local in time. So what you have to remember here is that actually these both learning rules will enforce correlation between pre and post-synaptic activities. They can be seen as Hebbian learning rules, yet their implementation is very different. And so that's what we did in this comparison here. So left STDP, right SDSP. And because STDP is not local in time, you have to compute inside each synapse a time window to compute the difference between the pre and the post-synaptic spike. So that leads to a huge overhead because it has to be replicated inside each synapse. And there are 100 to 10,000 of them per neuron. So that's really a big overhead. And next, for SDSP, you do not need to do that. Actually, all the computation is done in the neuron. At each presynaptic spike, you look into the state of the postsynaptic neuron. And that means you amortize a lot of computations directly in the neurons. So this learning rule is much cheaper. And also, if you want to go for time multiplexing, that's the same, because STDP, one way to implement it is to also make it local in time. The only way, and this is a solution that has been found in this paper, is to implement custom dual port SRAM memory. So you update the weight at each presynaptic and postsynaptic access. And therefore, you need to design a custom memory. That means design time overhead, and that also means density overhead. While for SDSP, you just need to look into the state of the postsynaptic neuron at the time of the presynaptic spike. So only a presynaptic access is sufficient. So it's a standard row-based access for Foundry single port SRAM. So these memories are usually high density, and that can indeed lead to record synaptic densities. And we'll show that in the neuromorphic chips that we propose. So this is exactly the purpose of the next part of the presentation. So going to silicon integration and demonstrating these density advantages. And so far, let me check the Q&A if there are.
There is a question, yes.
Yes. In slide
I can
9.
read it if you want. So So the question is about what's referred to by when you say biophysical diversity, right?
Yes, that's a good question. So actually, for the synapse, you may want to consider the plasticity. For the neurons, you may want to consider the behavior. That's a choice that we make. But again, you see that this choice is not innocent. We can make other choices. For example, if the deeper we go into the complexity, for example, you can see that synapses can have plasticity at different time scales. And that leads, if you want to implement all of them into synapses, that leads to also a lot of overhead. So as you can see, this is really implied by the phenomenological modeling approach. You have to decide what are the behaviors you want to go for. If you want to really emulate your model at the deepest biophysical detail, and then for that way, the subthreshold analog is usually the best way. And if you want to implement the key behaviors that you decide are the key behaviors, you usually go for a phenomenological modeling approach. And that will give also, to me, a nice link to the perspectives at the end of the presentation. So I hope I answered your question, but otherwise do not hesitate to continue posting on the Q&A, and I'll come back to this.
I also have one question myself, if you don't mind. It might
Sure.
come later, in which case I'll just be patient. But you talked about the local learning rules, right? But how do you leverage those to kind of learn the task you want to learn in the end?
That's a very good question, and I also come back to that later in the talk.
Okay,
so I told you
No.
the problem in bottom-up approaches is that it's really not easy to leverage these local learning rules to achieve a competitive advantage. And I'll make the bridge to that when coming to the top-down approach.
Looking forward to it. Thanks.
And so also a comment that I could make here is that, so these are only local two-factor learning rules, but there are also a huge increase in the popularity of so-called three-factor, four-factor learning rules, and I'll also come back to that in the perspectives. So now back to the silicon integration. So now we will implement these phenomenological models directly into silicon. And for that, we propose two neuromorphic processors, the first one of which is ODIN. ODIN stands for Online Learning Digital Neurosynaptic Core. It's an open source hardware, so you can look up, take the Verilog code, implement that on an FPGA if you want to modify it. And so far, the core, the neuromorphic processor embeds 256 neurons, 64K synapses. And you go for a time multiplexing approach here. So here's the neuron core. You've got the phenomenological Isaacevich update logic that we have proposed for the neurons. It's here. All the states of the neurons are stored into local memory. We decided to also choose to implement to choose with the update logic of a single leaky, integrate, and fire neuron. That is a standard one in neuromorphic community. And for the synaptic core, you've got the SDSP update logic for plasticity and all the synaptic weights that are there. And so if you look here, this is the chip microphotograph. So ODIN is only the small block that is there. So with a zoom on the floor planning view that is here. It was fabricated in 28 nanometer FDSOI CMOS. And I won't look too much into the power and area performance because we'll look globally at the state of the art afterwards. But I would like actually to point out, so these metrics are quite good. Usually what is shown in the papers, we show the good metrics. What is more interesting is what is not shown. And for the ODIN, these not shown metrics are actually the routing flexibility and efficiency. So it's only a point-to-point, chip-to-chip link that is based on the standard bus for routing spice that is called address event representation. So that's not a scalable design yet. So that leads to fan-in and fan-out values for the neurons of only about 256. And you have seen in the biology, these can be from 100 to 10,000. So this is not yet biophysically realistic. And another point is you see that most of the area is taken by the synaptic weights. And we have 4-bit weights so far. And so what if we could go to binary weight resolution? And if so, how do we manage the plasticity updates on binary weights? And to solve these two questions, so routing flexibility and online learning, we have proposed a second chip that is called MorphIC. So MorphIC is really based on the architecture of ODIN at the core level. So the core level is quite similar, but we have made a few modifications. For example, now it supports a stochastic version of SDSP to carry out weight updates on binary synapses. And we've included a routing infrastructure that also goes hierarchically to the chip-to-chip level. So this is a 4-core design. And the hierarchical routing infrastructure combines mesh-based routing, chip-to-chip, star-based routing, core-to-core, and inside the core across bar infrastructure. So that means you can really tile up chips in all 4 directions without requiring any external router or mapping table. And so that allows us achieving fan-in and fan-out values in 1K and 2K, and that's much closer to what is at hand in biology. So the chip microphotograph is this one here. It was fabricated in 65 nanometer CMOS. And again, I'll just skip everything related to power and area because that's the purpose of exactly what we want to do now, a state-of-the-art comparison. But the problem in the neuromorphic community usually is that these measurements are not standardized, especially as when it comes to power. So you end up with huge tables with a lot of hypotheses to try to compare everything on the same grounds. So for this presentation here, I simplify a little bit and we'll go through the most salient features in the table. So first, one thing that we can do is to compare ODIN, so the first neuromorphic chip that we propose, to the True North chip from IBM. And this comparison is very easy to make because both chips were fabricated with the same technology node. They have the same number of neurons and synapses per core, and these cores have roughly the same area with only about a 10% advantage for ODIN. So that means we can compare functionalities and features really one-to-one. And when it comes to synapses, ODIN embeds 4-bit with learning, True North 1-bit without learning. When it comes to neurons, 20 Isaacevich behaviors for ODIN, 11 Isaacevich behaviors for True North, but you can reach a 20 Isaacevich behaviors here if you combine 3 neurons together. Energy per synaptic operation, so the SOP here is about half that of True North, yet connectivity is not yet good, point-to-point AR link, against a large-scale mesh structure for true north. But that's exactly the point that we have addressed with MorphIC. So if we look now into the state-of-the-art globally in leaf true north, we can compare all the chips regarding neuron and synapse density. And we demonstrate with ODIN and MorphIC that they have the highest neuron and synapse densities among all spiking neural networks with embedded synaptic waste storage. And furthermore, they embed online learning. And when it comes to power, when it's compared to digital spiking neural networks, ODIN has the lowest energy per synaptic operation among the digital spiking neural networks, but MorphIC keeps also competitive energy efficiency. And now what is interesting is to compare to mixed signal approaches, because thanks to this direct emulation approach, they are really intrinsically efficient, extremely power efficient. And if you look here, you need only per synaptic operation, excluding leakage, and I'll come back to that, only about 100 femtojoules per synaptic operation, while it's more about 10 picojoules for digital design. So these ones are really much more efficient. But when you take the global network operation and leakage into account, it actually scales to 30 picojoules. So the global metric is actually not that competitive compared to digital, but that's for a simple reason. These chips were still fabricated in an older technology node. So this is expected to really go down with a more advanced technology node. And therefore, the key takeaway message that we could make here is that you would go mixed signal subthreshold analog if you want the best power efficiency in biological time. And for digital designs, if you want to have a very good power efficiency in accelerated time, this is the way to go. But still, the difference at the network level is not by orders of magnitude. And so now, before leaving the bottom-up approach in general, let's look quickly at some benchmarking results on a benchmark that we have proposed in this paper, actually. And so it's a sensor fusion benchmark, so where we combine information from an EMG sensor and a DVS sensor. So this is a spiking neuromorphic retina. And you combine the sensory information from these two sensors to classify gestures, 5 gestures that are shown here. And this dataset is available in both spiking and non-spiking formats that are equivalent. So you're very welcome to add the benchmarking of your TinyML system to this one. For now, we have benchmarked it on the Intel Loihi system, on the system combining the ODIN and MorphIC chips, and on the NVIDIA Jetson Nano portable GPU. So if we go into the results, let's look at here first. On the ODIN and MorphIC system, we classify EMG data on ODIN because we have more synaptic weight resolution. We classify DVS, so vision data on MorphIC because you have more synapse and neuron resources. And you see indeed that by combining both, we can get a boost in accuracy. And so therefore, the accuracy energy trade-off is here. You've got about 90% classification accuracy for 37.4 microjoules per classification. For Loihi, it's more like the high-cost approach. You get a much better accuracy, but also at a higher energy. But in both cases, you see that it really outperforms the portable GPU that is shown here as a software approach. And I would be tempted to say, of course, unfortunately, they are better than a general purpose GPU because these are still more specific systems, as we would expect from dedicated hardware. So now the question is, can we be more efficient than conventional machine learning accelerators that this community is used to? So can we demonstrate a competitive advantage? So I'll come back to that in the perspectives, but I also go directly into that in the top-down part of this presentation. That will be the purpose of the next section. And so far, it seems that the Q&A is...
There's one question from one of the other panelists of today, and the question is, it's from Hector Medina, I think. The question is, once phenomenological models are developed, is there ongoing research to convert them to more exact analytical or fundamental models?
If I get your question correctly, this is, I mean, if you go really for a fundamental approach, I would be tempted to say that you would better go subthreshold analog. But if you have, actually, I may have some slides to rewind. But if I come back to the architecture of ODIN, if you want to change a neuron model, that only requires an update in the update logic. And so if you want to have yet another model that you think is more fundamental or analytical and embeds much more functionalities that you would like to experiment with, you actually just have to add one more update logic and you can experiment with it directly. So I hope I did get your question correctly. Otherwise, please do not hesitate to continue asking.
Thank you. That's all the questions for now.
All good then. So for the top-down approach, 2 steps. First, the algorithms and then the integration. And our use case here is really adaptive edge computing. So you want adaptation at the edge. And if you want adaptation on chip, you really have to minimize the cost of neural network training at the edge. And when it comes to neural network training, usually backpropagation algorithm is a good starting point. So backprop has, interestingly, 2 key issues that are the same issues that prevent the biological plausibility of backprop and its hardware efficiency. And these 2 issues are the weight transport. So it's really the symmetries required between weights in the forward path and weights in the backward path. You really need to access the transpose of this weight matrix. So that's not biologically plausible because synapses are unidirectional. And that's not hardware efficient because that implies specific memory accesses patterns and therefore memory architectures. The second issue is the update locking. So for example, if you want to update this weight matrix here, you have to go for a full forward pass followed by full backward pass before you can update this matrix. And therefore, that means from biological plausibility point of view, all synapses are updated in real time and in parallel, so that's not plausible. And from hardware efficiency point of view, that means that you need to store locally in each layer all intermediate results. And so that means a buffering overhead for your implementation and also a latency overhead because you have to wait before the update can be done. And if you go for a pipelining scheme, that also leads to overheads in power and area. So that's the 2 issues that we have to solve. And if we look into the solutions proposed in the literature, you have, for example, the feedback alignment algorithm. So you just replace in the backwards pass the weight matrices with fixed random connectivity matrices. That still provides learning, and fortunately, it's released the weight transport problem, but not update locking. You have also the direct feedback alignment algorithm that uses as estimates of the layer-wise gradients projections of the output error through fixed random connectivity matrices again. So again, that solves the weight transport problem, but still not update locking. Although, as you can see here, the latency to update in the backward path can be made shorter. And therefore, we ask ourselves a simple question. What happens if instead of projecting the error, we project the sign of the error? And actually, something interesting happens for classification problems. For classification, usually your last layer is a softmax activation. So that means it's strictly bounded between 0 and 1. And if you compute the sign of the error, you have that the error is the difference between the target vector is just a one-hot encoding of your classification labels, and the output of the network that is strictly bounded between 0 and 1. And so you see here for the correct class, it's 1 minus something strictly bounded between 0 and 1. And for the incorrect classes, it's 0 minus something strictly bounded between 0 and 1. So that means that the sign of the error is known in advance for classification problems. And so that means that we can use this target vector, this one-hot encoding of the classification labels, directly as a proxy for the error sign. And that's the algorithm that we propose, direct random target projection. We directly project this target vector through fixed random connectivity matrices to estimate the layer-wise gradients. And therefore, that means you can release the weight transport problem and the update locking because you do not need to wait for the information of the sign of the error. It's known in advance next to the input image data. And so that means along all of these algorithms, you really minimize the computational and the memory cost up to the point that, interestingly, here you end up with a feed-forward local training algorithm. And so that's a good sign for our adaptive edge computing use case, because that means that this DRTP algorithm can be implemented at very low power and area overheads for an on-chip implementation. And also datasets representative for this complexity associated to smart sensors, to edge computing, I should say here extreme edge computing, is still on the order of MNIST and CIFAR10. So we really talk about here small battery operated devices that have to run at extremely low power. And so if you wonder whether the RTP scales to ImageNet, that's probably not the right question. And I can already answer that wouldn't work very well, but still it worked reasonably well on MNIST and CIFAR10. And so I won't dive into the numeric details of a comparison of the RTP against backprop, feedback alignment, and so on. In this presentation, we'll directly show these claims into silicon. So that will be the purpose of the next section. But before that, I would like to just make a small comment as to neuroscience And interestingly, the RTP is biophysically plausible, not only because it released the weight transport and the update locking, but also because it could come in line with some of the mechanisms at hand in the brain, more specifically in some cortical areas where we found the existence of output-independent target signals. That's exactly the case for the RTP in the dendritic and circuit pathways of intermediate layer neurons. So I'm not saying the RTP is the way the brain learns. It comes in line with some of the mechanisms that the brain uses to learn. Okay, so that's all for the algorithmic part. Let's see if there are some questions here. See, there's a question for the RTP.
Yes, there is one. Yeah. So
how do you determine which layer neuron weight need to be adjusted and by how much? Since you only have the sign, yeah, that's a very good question. We only have the sign of the error and not the magnitude of the error. So that means that compared to direct feedback alignment, you lose two things through the error magnitude. You need the global magnitude of the vector, so that means there is no modulation of the learning rate as the learning progresses. So usually when you learn, you have that the error goes down, so the magnitude of the error goes down, and so that modulates the effective learning rate. So the steps that you will take will be smaller. That's something that you can recover with the RTP through a learning rate scheduler. So that's not too much of an issue. But really the source of performance degradation of the RTP is that you lose the information of the relative class-to-class magnitude. So for example, you can have a big error for one class and a smaller error for another class. And this information you do not recover. And perhaps also another aspect in your question is how do we determine which layer or neuron needs to learn? And as you expect, because there's not this magnitude modulation, the RTP tends to go really full scale in one direction. And actually the way the RTP stops learning is through the saturation of the activation function. So that means the ReLU activation that has no saturation won't work. But for example, if you use TANH that saturates below and after to kill the gradient when, for example, the activations go full scale, that's a good way to implement stop learning in the RTP. And actually the experiments that we report use this TANH activation function in the hidden layers. So that's a good question. And for the further details and all explanations, I would direct you to the paper where we analyze these effects that you refer to.
Thank you. That's all questions for now.
Okay, so now the last part of the presentation, the silicon integration. And so let's take a step back in our top-down methodology. So our real-world application, adaptive edge computing, the algorithm we have chosen the RTP, but still this big challenge, what do we consider as the bio-inspired elements that we want to implement? And what we chose as the key features of bio-inspired computation is three factors. It's sparse, it's event-driven, and it's time-based. And therefore, it makes sense to really start from spiking neuromorphic retinas that have an output such as the one shown here. So when you move the hand in front of these kind of sensors, you will have that the pixels individually that have changes in temporal contrast will emit a spike. So when there is a temporal contrast change higher than some threshold, each pixel individually will decide to emit a spike. And so when you have a pixel that emits a spike, you can directly project your convolution kernels to the feature map elements that this input pixel maps to. So that really means you can carry out your convolutions in an event-driven manner. And one more thing, if you really want to enforce this sparsity, that is a hallmark of spiking neural networks, you can actually assume, so that's an assumption that's not a pre-processing, and that the inputs from such sensors is encoded in a time to first spike manner. So what that means is that we assume that the pixels with the highest change in temporal contrast will spike first. And you see here when the hand moves in front of the camera, these pixels that have the highest temporal contrast changes, so in other words, the edges spike first. And so that's a reasonable assumption that we can verify later, but that can lead to actually the use of very few spikes to lead to a classification, as opposed to a more standard rate-based coding approach, where you need to accumulate a lot of statistics before you can carry out an inference. So after some time window that corresponds to the time constant of your time to first spike encoding related to the stimuli of your environment, you can carry out your max pooling in a frame-based manner because all the elements are really available in parallel. And then for the fully connected layers, we propose here to combine frame-based processing and event-driven processing. So in other words, input-driven and output-driven. So we go through each of the hidden neurons one at a time. We compute the activation of that neuron and we project it directly onto the output layers. So that's convenient because at least you can pipeline the processing of these layers. We minimize the memory accesses and we maximize data reuse. So that minimizes power. And that's also very convenient for including our DRTP updates here. And so overall, we end up with an event-driven CNN, or ECNN for short. And more specifically, we end up with SPOON. SPOON is the third neuromorphic chip that we propose. It stands for Spiking Online Learning Convolutional Neuromorphic Processor. It has 10 5x5 kernels for 32 by 32 input images. Fully connected layers are 128 neuron and 10 neuron. And the thing that I really want to emphasize is that it relies on time to first spike encoding. And so that means that you need to have access to a time constant somewhere that relates to the stimuli you are interested in. So it can be either provided externally through some tick or generated internally in a configurable manner. So here's a cheap microphotograph of SPOON. SPOON is only the block that is shown here, fabricated in 28 nanometer FDSOI CMOS. And the key message to see in this table is this one. So we wanted to show that the RTP is a low overhead algorithm. That's really the case. The overhead of embedding this algorithm is only 17% in power and 12% in area. So that really means this DRTP algorithm is a low cost, almost for free when you implement that on chip. And so we benchmark SPOON on the MNIST and Neuromorphic MNIST datasets. Neuromorphic MNIST is when you show MNIST images to a neuromorphic spiking retina. So you move the retina in front of the images so that it can generate a spiking version of the images. And that's a useful dataset for us to verify our assumption of time to first spike encoding because it works just well. So a few remarks here. So the power numbers are still pre-silicon numbers. So the chip is back, it's functionally validated. We are in the process of extracting the final energy matrix. So it's not yet updated, but in other words, stay tuned for the journal extension. And now what we are really interested in is to compare SPOON to conventional machine learning accelerators. And for that means that for the comparison that is next, we will choose the MNIST dataset because it's the only one that provides information for all of these conventional accelerators and with SPOON. We have data and benchmarking data for all of these platforms. So if we plot these results into some trade-off between accuracy, silicon area, and energy per inference, you see actually that the best chips will tend to go on the top left. And the first thing that should strike you is that spiking neural networks are shown in gray here. And therefore, that means that they really lack in efficiency behind their conventional machine learning accelerator counterparts. So ANN, CNN, even binary neural networks. So that's the first thing. But for example, MorphIC here, it's on the same ground for the accuracy energy trade-off. But it does have some advantage in the accuracy area trade-off. But what we are interested in now is in SPOON, and the SPOON results are here. So here you see the accuracy results that you obtain with on-chip DRTP, and here the accuracy results that you can obtain with off-chip training when you program the weights directly into the accelerator. And therefore, what it means is that you can recover this gap in accuracy energy trade-off, and it achieves also a very efficient trade-off between accuracy and silicon area. And so that means the key claim is that only SPOON allows reaching the efficiency of artificial neural network, convolutional neural network, binary neural network accelerators, while enabling online learning with event-based sensors. And that's really one unique feature of SPOON. And so that's all for the top-down part. Let me check also if there are questions again.
There is one question on SPOON, where the question is, what do you mean by computation is time-based? Is it time-based because of the data input or in another way?
Yeah, so that's a good question as well. So usually it all depends on both the processing and the input data. So for example, if you consider images, static images, there is no time in the input data. And so if you want, for example, to compare MNIST, to compare platforms on MNIST, either spiking neural network or conventional neural networks. So that means you compare these platforms on some data that does not have a time dimension. And that is exactly going to be one of the next parts of my presentation, is that spiking neural networks, as they compute with time, they are able to leverage time, are not likely to show an efficiency advantage on data that does not have a time dimension. But for example, if you want to classify movement, if you want to classify biosignals, if you want to classify keywords, keywords in speech, these have a time dimension into the data. So that's the time dimension in the data. But for spiking neural networks, you are also different codes. And for example, the most famous ones is the rate code. So for example, that means that you encode a pixel value into the rate of the spike train. And so that leads to a very inefficient use of the spikes. So each spikes only encode a marginal amount of information bits, if you want, as opposed to the time to first spike code that can potentially encode an arbitrary resolution. So it depends on your time resolution, but an arbitrary resolution into the timing of a single spike, if you see the nuance, as opposed to the frequency of a spike train. So I hope I have been clear here. Otherwise, also please let me know.
Thank you. I also have one question on this benchmark graph you have there, right?
Yes.
There's a few other designs in literature, which, for example, True North is one, which have multiple kind of accuracy and efficiency trade-offs that they can have in a flexible way, right? With this kind of approach like Spoon, is that something that's possible as well?
Yeah, so exactly. Actually, you see that these different points for True North is actually a different number of cores each time. Mm-hmm. So Spoon is really a small scale proof of concept chip. So it's not yet scalable. But as we have seen in this diagram here, actually you can modify this diagram to hopefully, for example, tile up several Spoon chips, either for different patches of the image. You can carry out majority voting in the end. You can carry out classifications on subsamples of the image. So here the Spoon scale is a proof of concept chip. Of course, it's only 32 by 32 input images, but that's also the same for most of the other accelerators that are shown here. It's also for proof of concept 28 by 28 or 32 by 32 input images. So True North indeed has the luxury of having it was 4,000 cores inside a single chip. And of course, you can go really large scale with these. And so that's what we did. We tried to compare the number of cores that are comparable in scale with the dedicated accelerators, which are also small scale proof of concept. But of course, if you want to derive that to a real product, you would have to work on the scalability of the system depending on your application.
Thank you, I understand. Thank you.
And so now, time for the conclusion and perspectives. So we investigated both the bottom-up and the top-down approaches. On the bottom-up side, the conclusions, while trying to improve this versatility efficiency trade-off with our ODIN and MorphIC chips, together with a phenomenological digital approach, is this one. That's the first claim that we have, is that hardware-aware neuroscience model design and selection allows reaching record neuron synapse and neuron synapse densities with low power operation for large-scale silicon integration. So next, we investigated the top-down approach, improving this accuracy efficiency trade-off for adaptive edge computing with on-chip training thanks to DRTP and or Spoon chip that implements also this DRTP algorithm. So the second claim that we have is that combining event-driven and frame-based processing with weight transport-free update unlock training supports low-cost adaptive edge computing with spike-based sensors. And therefore, if we take a step back and would like to see what's going on between the bottom-up and the top-down approach, we can have that the top-down guidance helps pushing bottom-up neuron synapse integration beyond the purpose of neuroscience experimentation platforms. So what that means, it really means that you need top-down guidance to cross this efficiency gap to achieve a competitive advantage with neuromorphic systems on real-world tasks. And the other one is that bottom-up guidance supports top-down design towards brain reverse engineering. So as to this question of which bio-inspired elements and primitives you take, bottom-up guidance is really necessary to uncover them and to distinguish them from artifacts that are induced by evolution to compensate for the non-idealities of the silicon of the biological substrate. And therefore, now if we want to have the key primitives as to what's next, more globally for neuromorphic engineering and spiking neural networks, I think the question is not anymore, can we make it work, but will it bring a competitive advantage, and hopefully not only against general purpose GPUs. And therefore, as said earlier, thanks to one of the questions, is that we need something better than MNIST for benchmarking. And therefore, I think really keyword spotting at the edge and biosignal processing can make neuromorphic shine, especially because they embed a time dimension, and therefore we can leverage sparsity. That's maybe a word that I haven't used enough to answer the previous question, and not only in time, but in biological time. And for these, for example, a direct emulation approach can really be promising. And therefore, that brings me to the next point, because I told you that digital, phenomenological digital is really a pragmatic way to go, pragmatic and efficient, and that's really a very good short to mid-term approach. For the promising avenues, we may really want to solve this question, leverage the variability of the subthreshold analog design, and possibly also fine-grained mixed signal design. So not only just analog at the core, digital at the periphery, but maybe we want to co-integrate both and leverage at a finer granularity the advantages of both. Also, if we take a step back in the bottom-up and the top-down approaches, bottom-up, the trend is really going into the dendrites. So in this presentation, I only talked about neurons, synapses, but there are really dendrites, and it's a powerful primitive. And also the top-down trend is there's a whole new wave of training algorithms mapping onto bioplausible primitives with a few examples here. So this is really an exciting direction. And then the final, more open question is to whether we can achieve cognition without a body to interact and adapt to the environment. And that can make a case for neuromorphic robots, as actually discussed in this paper. So I would like to acknowledge, because most of this work has been carried out during my PhD at UCL Louvain, so I would like to acknowledge the support of my supervisors, Professor David Boll and Jean-Didier Legat, and my key colleague Martin Lefebvre, with whom the DRTP algorithm was designed. And now I'm happily pursuing all the perspectives shown in the previous slides in my postdoc under the supervision of Giacomo Indiveri and with many great colleagues and friends. So here are the references in this presentation. I would really like to emphasize this one because it was released just like last week. It's a big review of all bottom-up, top-down neuromorphic processor design, the trends, the benchmarking. So it contains what has been said in this talk and much more discussions as to design guidelines, for example. So I would like to emphasize this one, links to the open source projects of DRTP and ODIN. And also ways to contact me. So I'll answer questions now, but do not hesitate if you have more questions to send me an email or a message afterwards. And I would like, of course, to again thank the committee for giving me this opportunity to talk about my work.
Thank you, Charlotte, for the very, very nice and interesting talk. There is one more additional question from Rajiv Ranjan in the Q&A. He's asking about what the percentage of the chip is in SRAM memory.
So I guess
I think it refers to spoon. Yeah, I guess
so. So yeah, indeed, it's not shown here. As far as I remember, but I may want to, no, it's not shown here either. So I would say at least 50%. But I would need, so if you check the paper, there's a detailed, so it's in this ISCAS paper, there's a detailed floor planning view. This reference here. Yes, and published in 2020. So there's a detailed floor planning view where the SRAMs are highlighted. So I'm just speaking by memory about 50%, but if you check in the paper, you will get the number, the accurate number.
Excellent, thank you very much. And then it looks like there's no further questions anymore. So thank you again, Charlotte, very much for this talk. Of course, I do want to thank all our sponsors. So the premier sponsor, Newton, with their automated TinyML solutions. Executive sponsors, ARM, and we organized also a very nice panel that we witnessed just now. Edge Impulse as well. Jan was there and presented some of their work just now as well. Then also Qualcomm, working on advancing AI research to make efficient AI ubiquitous. Sentient, working on chip solutions to do ultra low power, high performance, deep neural network processors. Then our platinum sponsors, Infineon, we've had a keynote from Wolfgang from Infineon earlier today. Reality AI, working on advanced sensing with Edge AI and TinyML. Then our gold sponsors, Latent AI, working on adaptive AI for the intelligent edge. SensiML, building smart IoT sensor devices from data. And then our silver sponsors, EMSA, where Ilat also presented today, what they are up to, Green Waves Technologies, HOTG, Imagimop, Kiso, SEED, and ST. And with that, that's the wrap for today. Thank you everyone for your attention and your attendance.